equilibrium, but also causes relative perm changes in a reservoir. This is very important because not only do we assume reservoir equilibrium on almost all of our reservoir simulations, we actually assume it in our selection of drill fluids, in our selection of cementing fluids, in our selection of completion fluids, and it can cause us some dramatic changes in reservoir flow if we don't recognize non-equilibrium. Geology controls equilibrium. Some of the geologic mechanisms causing reservoir non-equilibrium are burial, uplift, or overburden erosion after the reservoir has been charged. These processes change the temperature and pressure of the fluids, which in turn changes the energy equilibrium in a reservoir. For example, in the western North America, at the end of the Miocene, the beginning of the Pliocene, western North America was uplifted 5,000 to 10,000 feet. Erosion has continued to the current day. The rocks run down the Mississippi River and have given us all these great tertiary reservoirs in the Gulf of Mexico. But in the meantime, we've changed the energy equilibrium in western North America. And so almost all of the western North American reservoirs are not in energy equilibrium. So let's look at an example from Montana. This is a shut-in pressure plot on a 10 millidarcy carbonate reservoir. And it starts out doing what we all expect when we shut it in, pressure buildup. And then it rolls over and it starts to decline. Now mostly when people get this kind of data, they throw it away because it doesn't meet our assumptions of what a shut-in curve should look like. And because it doesn't, if we try and match it with the standard assumptions, this is a reservoir build-up modeling program that assumes equilibrium, we get a horrible match. And we don't really know what to do with that. But if you use a model that does not assume equilibrium, that's a pretty decent match early on. Now, the problem with this particular algorithm is that it assumes a single diameter capillary tube. And so in late time, as more and more pore networks start imbibing fluid, you can see the breakdown in the correlation, but it's a very good match while we're just imbibing water into a single tube. So what has happened here is that as we shut this reservoir in, instead of pressure buildup by a fluid coming out of the reservoir, we start imbibing fluid into the reservoir and the pressure drops, the bottom pressure drops. And that's a very different phenomenon than we expect. It also means that in restoring that equilibrium by imbibition, we have a very, very hard time getting that water to come back out of there. And it blocks off the oil or the hydrocarbon phases, and we can't move it, and so the water starts moving. In this particular example, we went in and injected a surfactant, carbon dioxide, into the reservoir after we had imbibition. And we can look at the pressure results from there, and we see about a 600 or 650 pound drop in pressure as we inject CO2 in. That tells us that that skin on that reservoir was across the oil pore network was about 650 pounds. That's how much additional delta P we need to put on that reservoir to get that interface to move. So it now takes 650 pounds of additional drawdown to break that interface and start moving the oil and gas. If it only takes 400 pounds of additional drawdown to overcome the capillary forces and start moving the water in this reservoir, guess what? I just took an oil reservoir and by relative perm damage made a water reservoir out of it. And that happens all too often in Rocky Mountain reservoirs. And that's something I was dealing with. I was getting 100% oil tests on drill stem tests and coming back and completing for 90% water in some of the projects I was working on. And of course what happened was, the time you ran the drill stem test, there wasn't enough time to imbibe water enough to damage it. By the time you finish drilling, logging, running casing, cementing, perforating, there was enough time to do that damage, and we were changing the relative permeability of the reservoirs. Models are useful if they properly represent the geology, chemistry, and the physics of the real world phenomena. We need to continually circle back to first principles to understand, is this model useful? Controlling variables in multi-phase flow in oil and gas reservoirs are reservoir architecture, energy at the interfaces, interfacial tension, and energy equilibrium, something that we never, ever, ever consider. I, in my 40 years, have never had somebody walk up to me and ask me, is this reservoir in equilibrium? And it's a critical thing to understand, not just from a modeling simulation standpoint, but from a drilling and completion standpoint. Reservoir architecture can be highly variable and can be only determined by visual examination of the reservoir. There are very few Kathy Stolpers in the world, but you need to really talk to your petrographer to really see what your pore throats look like. Even if you do an X-ray diffract, you go, oh, I got illite. Well, what is it? Is it pore ridging? Is it hairy? Is it detrital? You need to know that to determine what your reservoir flow characteristics are. Energy equilibrium is changed by geologic history. That's a question you need to ask the geologist. Has this area been uplifted and eroded? Has it been further buried? What's happened since I put oil and gas in this reservoir? And any attempt to model fluid flow in a reservoir needs to be continually refer back to the real world and determine the validity of the assumptions. So much of the math we use, so much of the assumptions that we make become secondhand. We don't even think about them. And we need to continually think about what assumptions have I made to make these decisions? And do they fit the real world? Because if not, difficult things can happen. Thank you.
Questions?
Questions?
I've got a question. Now, I mean, it's very, we know that when you, in some wells, when you drill and start producing those wells, they produce maybe more oil than water, and then over the lifetime of the well, you see changes in the oil-water ratio. Now, now looking at all this complex flow pattern you just explained, does that have anything to do with what is happening in the lifetime of the well?
Are you talking about increasing oil cuts?
Usually increase in water cuts.
Okay.
as time goes
Sometimes
on.
that's depletion. Sometimes that's relative permanent. A lot of these reservoirs, what happens is when I put them on production, my oil cut, my gas cut goes up in the well, my gas production goes up in the well. And what I'm doing in that situation is getting enough drawdown on the reservoir to start to pull some of that those interfaces out, overcome that interfacial tension and pull the oil out. So the water out of the way. So if you have a reservoir where you start off producing 90% water, and as time goes on, you're up to a 50% water cut or a 25% water cut, you're definitely in a reservoir that's not in equilibrium. One of the classics that's been done over the last 20 years is Kearney Field in Oklahoma, where they go in, drill wells into the Hunton. They make 300,000 barrels of water before they start making any oil and gas. And they looked at it as a dewatering project. Well, no, it's not. It's a relative perm issue that you're correcting by putting enough drawdown on that well for long enough to get the water to move out of it. Okay, thank you.